Okay. So last time we talked about a way to construct fields from a modulo arithmetic of polynomials. Let me remind you. You take a field and in a prime polynomial I remind you that a prime polynomial, it means that f cannot be written as, let's say, f equals a times b, maybe do it with the variables, fx equals ax times bx with degree of a and degree of b strictly bigger than 0. I mean, so they are not constant polynomials. And we looked at we denoted it as f sub f of x. I guess in our notation last time, maybe it's better to keep it. We took phi for the prime polynomial, and then we defined f sub phi to be the set of all, you can call it remainder polynomials. So let's say Rx equals sum of ai x to the I equals 0 up to k, where the AIs are elements in F, and k is strictly smaller than n. So this is like remainder polynomials, remainders of mod phi arithmetic. And we showed, so this in fact it can be defined for any phi without requiring that it's a prime polynomial. But if it's a prime polynomial, f sub phi is a field with I mean mod phi addition and mod phi multiplication. Now, how many elements does this field have? Can anybody say? If suppose F is a finite field. So if the number of elements in F is some, it doesn't matter. I mean, let's say it's some T. How many elements does this F sub phi field has? No one? It's supposed to be a very easy question. So what are all the possibilities to get polynomials of this form R? I mean, you need to choose. Basically, you can write. You can always write R as a sum I equals 0 up to n minus 1 ai x to the I, where the ai's in F, but possibly some of them are 0. So if it is a polynomial of degree 2 and n is equal to 4, then you can extend it to a form of this way, where you take a3 to be 0.
Is it p to the raised power n?
Yes. So the number of elements in F sub phi is t to the n. Okay. Is this clear? You were quite slow in answering this. So, you know what? Maybe because I feel that you are not exactly on the same page, let me do an example. We did it last time, but it may be good to do it again. So I take F to be the field of two elements, and phi is the polynomial x squared plus x plus 1. I claim that phi is prime. Phi is prime since, well, prime, of course, you need to specify over which field, over F2. And the reason is that it has no roots. I mean, this you can check by hand. You substitute 0 into phi, you get 1. You substitute 1, you also get 1. So it has no roots. And every non-trivial decomposition of a polynomial of degree 2 must be two polynomials of degree 1, which would imply that it would have a root. So in this case, a polynomial of degree 2 is prime if and only if it has no roots. It's not true in higher degrees, but and so now I can look at F sub phi. f sub phi actually, as a set, it does not depend really on the specific definition of phi, only on the degree of phi, because I take all the remainder polynomials, Rx equals, we can drop the sum. So here I have a0 plus a1x, where a0 and a1 are some coefficient in the ground field. Right? This is all the possible remainders of doing a long division of a polynomial by phi. So, but let's be more specific. What are the possible polynomials? I mean, I have the zero polynomial. Then I have the polynomial 1. And then I have the polynomial x and the polynomial x plus 1. And that's it. Right? So you see, as a set, you could choose any polynomial of degree 2, and the set f sub phi would be the same. But of course, if you choose a different polynomial phi, then the arithmetic on n sub f sub phi would be different, because the arithmetic is doing long division by by phi. Okay, so let's construct the multiplication and addition table. Addition table is you don't need to do any modulo phi, because this set of remainders, when you add two remainders, the degree of the result is still strictly smaller than the degree of phi. So whenever you do mod phi for something with a degree strictly less than the degree of phi, you get the thing itself. It's like, again, the analogy with integers. I mean, if you take some k smaller than n, then k is equal to k mod n. You don't need to do any modulo in this case. So when I do addition of two polynomials, I do addition as I'm used to in polynomials. So let's say 0, 1, x plus 1, 0, 1, x plus 1. And you would get, for example, if you do x plus 1, then this is 2x plus 1, but 2 is equal to 0, so this is 1. Okay? And you can fill in the addition table. The multiplication table is a bit more interesting. I guess I don't want to write all the multiplication table, but note that if you take x squared, then it is equal to minus x plus 1 modulo phi, because I remind you that phi is x squared plus x plus 1. So this would mean that, and now what is the negative of, I mean, minus x plus 1 of course, in F2 is simply x plus 1. Okay, so I get that x times x is equal to x plus 1 in the mod free arithmetic. And similarly, you can do x cube, and you will get 1 modulo phi. Okay, so this is how you work with these fields. Any questions about this? I feel that you are not completely fluent, but I need to hear what is not, what may not be clear. Okay. So it may be good to introduce a new notion. I'm trying to be very careful in doing these things, but I think here is it's a good. I mean, it's convenient to have it as a terminology. So a set R. Or let's say a ring is a set R with specified elements zero and one, and two binary operations here plus from the Cartesian product to R and multiplication that satisfy all the axioms of the field, of a field, all axioms of field, except, well, possibly existence of a multiplicative inverse. And well, the easiest example is the integers, right? The integers, you have addition, you have multiplication, but you don't have a multiplicative inverse. You have an additive inverse, but you don't have a multiplicative inverse. In fact, if you take the integers modulo n with addition modulo n and multiplication modulo n, then this is also a ring, right? You have an additive inverse for every element, but you don't necessarily have a multiplicative inverse. And yes.
Can you provide some intuition why it is useful for us to have something that is almost like a field, but without multiplicative inverse.
Okay, so that would be the next example. If F is a field, Fx, I mean polynomials over F is a ring. Right, because you can add two polynomials. You have an additive inverse. I mean, if you take a polynomial F, then you just do minus over all the coefficients. That's the additive inverse. But you don't have a multiplicative inverse. And if you, I mean, if you want the kind of the conceptual reason that it's good to have this terminology in our toolbox, what we did, if you remember, when we proved that ZP or it's sometimes denoted as FP is a field, is the way we worked about it is we first looked at integers modulo n, and we saw that you have addition and multiplication that are associative, and all the usual axioms are satisfied, except possibly the existence of multiplicative inverse. And then in order to get to ZP, we said, okay, what do we need for a multiplicative inverse? And the condition is that n is a prime. So it's convenient to have an intermediate notion, right? Because if you look at this definition of rings, then of course every field is a ring. So the set of all fields is contained in the set of all rings. And every ring is in particular an abelian group. So rings are kind of an intermediate notion between fields and abelian groups that allow us, on one hand, to talk about a structure with two binary operations, addition and multiplication, but slightly weaker than a field, so that they include, for example, these three examples that are not a field, but nevertheless have multiplication. Now, maybe the more interesting example is you take a field F and phi, a polynomial that is not prime. Okay, so then F sub phi is not a field, is a ring. Well, let's say not a field, but it is a ring with, of course, with mod phi arithmetic. Anybody remembers why in this case, when phi is not a prime polynomial, Why is this not a field?
Because we can't construct this multiplicative table where we can find a multiplicative inverse for each element.
But why don't we have a multiplicative inverse for every element? I mean, there is a very simple argument that, again, you should think of this as in the analogy to the integers. How do we prove that integers modulo n is not a field? We know that in a field you cannot have zero divisors. So if in a field you have two elements x and y, such that x times y is 0, then since if you're in a field, then you have a multiplicative inverse to x and y if they are not 0. So the only way that x times y will be 0 is if x is equal to 0 or y is equal to 0. It follows from the field axioms. And in integers modulo n, if n is not prime, then it is k times l for some k and l. And then k times l in Zn would be 0. So Lisa, right? You understand this? Why at least integers modulo n is not a field? What's the argument here?
I understand that if it is not prime, you can factorize it and represent as a product of the product of a prime polynomial with something else.
Yes, it doesn't matter even that it would be a product of prime polynomial. The fact, if it's not prime, then it is a product of two polynomials with with non-trivial degree, right? But then A and B belong. Of course, A and B have degree that is strictly lower than the degree of phi, right? Because that's what it means to be a non-prime polynomial. So if this is so, then both of them belong to f sub phi. Both of them can be viewed as remainder by long division with phi. And A times B is equal to 0 modulo phi, right? Because A times B equals to phi. So what I get is that I have two non-zero elements in f sub phi whose product is the zero element, and this phenomena cannot happen in a field. So I can it's kind of by abstract reasoning, I know that this cannot be a field. Is it clear?
Yeah.
Okay. But it is a ring. I do have addition, I do have multiplication. I don't want to throw it all away and just consider it as an abelian group, because I care about the multiplication. So this is maybe the justification for why it is useful to talk about rings, although we will not get into, deep into the theory of rings. So in this case, F sub phi is a ring. Now, there is a natural notion of what it means to be a ring map. For two rings, let's say R and S, a ring homomorphism is a function F from R to S such that, well, it has to preserve the specified elements, and it has to preserve addition and multiplication. So F of A plus B is equal to F of A plus F of B, and F of A times B is equal to F of A times F of B. And this is for every A and B in R. And if you wish, you can throw also the axiom that, but it really follows from these axioms that it commutes with additive inverse and multiplicative inverse. This is for every A in R. And of course, multiplicative inverse only exists for non-zero elements. So this is a ring homomorphism. It's like, basically, it's the same axioms of what it means to be a field homomorphism. And F is called an isomorphism if it is bijective. And just like in fields, F from R to S is a ring isomorphism if and only if there exists a ring homomorphism F minus 1 from S to R such that let's say F minus 1 composed F is the identity map on R, and F composed F minus 1 is the identity map on S. And this you can prove. This is kind of a recurring theme. This is a property that will always characterize isomorphism of every, basically of every notion that we will encounter. I mean, groups, fields, rings, vector spaces, and so on. So it's really, it should not come as a surprise. I mean, we saw this before. You can prove it as an exercise. Now, what happens in rings is just like in groups, you can talk about quotients. And the notation, we will denote F sub phi as Fx modulo phi. You can find it in the literature sometimes as Fx modulo the thing generated by phi. Okay, and this is analogous to the notation of integers modulo the subgroup of integers multiples of n. Right? This is the notation for a quotient group. So I do not, of course, as I said, I don't want to get into the theory of rings too much, but I do want to use this notation. I think it's useful for you as well, and a little bit. I mean, eventually, what we will need in what's coming up is just this notion of isomorphism of rings, and this will be enough. So, Lisa, do you feel that it's motivated enough?
Yes, thank you.
Okay, so don't be afraid. It's not complicated. Again, it's like fields. It's just that we are dealing with a kind of creatures like these polynomials that we want to capture something that has the. I mean, we want to be able to talk about a structure that has the addition and multiplication, but possibly without inverses, in order to kind of reason about these polynomials and polynomials modulo another polynomial. Okay. So now there is a funny meta trick. So consider a field F and a prime polynomial phi of x. Now, if the degree of phi is equal to 1, then fx, what we called f sub phi, and now I remind you, we have a new notation. This is by definition all the remainder polynomials of doing mod phi. But since phi has degree 1, the remainder polynomials have to have degree smaller than 1, so they have to be constants. So it's really all the A0 such that A0 is in F, which is of course just another way of saying F. So this is not interesting. I mean, we don't care about a mod phi arithmetic if phi is of degree 1, and of course if phi is of degree 0, that's even less interesting. So suppose that the degree of phi is strictly bigger than 1. Okay, that we know that the number of elements of fx modulo phi is simply the number of elements in F to the power of the degree of phi. Right? This is what we said here. Where was it? Right? If the number of elements in F is t, then the set of all possible remainders is t to the n, when where n is the degree of phi. Okay, so so we know the number of elements, but we can look. We can consider the ring homomorphism I go from polynomials over F to polynomials over F modulo phi, and the map takes a polynomial f of x and sends it to f of x modulo phi. I mean, just take the remainder of long division of f by phi. And we talked about it last time, that this is indeed a ring homomorphism, because if you take multiplication, I mean, if you do f times g would be sent to f times g modulo phi, but it is equal, in fact, to f modulo phi times g modulo phi. Right? And the same for addition. F plus g modulo phi is equal to f modulo phi plus g modulo phi. So this is a ring homomorphism. I call it a pi. This is sometimes called the quotient map. Now I look at so phi, or maybe put it like this. F is contained in fx modulo phi x as the set of constant remainder polynomials. Right? I mean, here, remember, we have this all remainders of the form sum ai x to the I with some limitation on the degree. Of course, you can just take the remainders that are just the constant a0, and this can be identified with f. Okay, so if I call this guy k, let me call it k. We can consider, we can view phi as a polynomial over k. Right? I mean, k is a field, so we can always talk about polynomials over any field. Here it's a bit perverse because we talk about polynomials with coefficients in polynomials, but this kind of meta trick is useful. So, I mean, it means that I can view the set of all polynomials over k. Now I put it with a big variable x to differentiate from the small variable that comes here. And I can view phi as a polynomial over this this new field k. Right? I mean, whatever phi was, I just now declare the variable to be capital X instead of lowercase x, and that's my polynomial. Is this clear? Yeah.
I have a question. So, because I don't see why, like, so you have, you define k as f of x over phi of x, like the set of polynomials, well, the field over the phi of x. But, and then you say that you can view phi as the polynomial over k. But if you evaluate phi over k, which is f of x over phi, like in my mind, I was following, but at this step, it was like, okay, phi is getting cancelled out because it's over model phi.
Okay, so that's I mean, how does a typical element in k k of x looks like? It's you can write it as let me call it R0 plus R1 x plus R2 x squared plus let's say Rn x to the n, such that R0 up to Rn are coefficients, right? They need to be elements in K. So, but K is the set of all remainder polynomials. I mean, so R0 up to Rn, they need to be polynomials. You could write, yeah. they would be polynomials over f in the small x intermediate or indeterminate. Let me write it slightly better. Rn x to the n, such that R0 up to Rn are polynomials over f with degree. Actually, n is maybe not good here because we already took n. So let me do, let's say, m. Such that the degree of each of the Ri is strictly smaller than n, because they need to be in K, and K is the set of all remainder polynomials R of x equals to sum ai x to the I equals 0 up to k, and k is strictly smaller than n, right? That's the set K. K as a set is the collection of all possible remainders by a mod phi. So polynomials over K are these formal sums. Now I just took the variable and made it a bit different. If you wish, it's kind of you can write it also. It would be a bit cumbersome, but you could also write R0x plus R1x times the capital X plus R2x times x squared, and so on. Okay, is this clear now? How to view
Yes.
polynomials over?
Thank you very much, because this made me see the thing. I mean, I was not seeing the right difference between the two, like the lower and capital X.
Yeah.
So thank you very much.
Yeah. So and now, of course, you have phi with lowercase x is some kind of a, let me just write it with coefficients, a0, a1x up to an x to the n, right? We said that phi is a polynomial of degree n. Now, a0, a1 up to an, they can be viewed as remainder polynomials. So phi with capital X is the same thing, a0, a1, but now I replace x by capital X. And I view all these guys, a0, a1 up to an, in K. I mean, I view them as constant remainder polynomials. Okay? And now there is a funny trick. Yeah.
And in phi with small x, all A were just field elements.
Exactly. So phi with small x, because phi is so a1, a0 up to an are elements in the field. But we said that the field can be included into the set of all remainder polynomials. Right?
Yeah.
Okay. Now watch this. I take, remember, we have this map pi from f of x to f of x modulo phi of x. This is all small x, right? This we call k. And I take pi of the polynomial small x. This is assuming that phi is of degree bigger than 1. This is x, right? Because if phi is of degree 1, of degree bigger than 1, and x, of course, is a polynomial of degree 1, then doing the modulo phi, you don't do anything. Just like if k is smaller than n, you don't do, I mean, k modulo n is simply k. Now, so I view this pi x as an element in k, and as an element in k, I can plug it, I can substitute it into a phi with capital X. So phi with capital X, substitute pi of x. It means that I do phi of pi of x right? This is, and this, of course, since phi capital X is a polynomial in k of x, capital X, when you plug in an element in k into phi, when you substitute an element in k into phi, you get again an element in k, right? Just like you take a polynomial over f, you substitute an element in it, and you get an element in the field. So now phi with pi of x is simply phi of x, lowercase x now. This is an element in k. It's supposed to be an element in k. But in k, phi of x is 0. So this is equal to 0 in k. So what we got is that pi x is a root of phi capital X, i.e. in k, I can write phi of x, or in k capital X, I can write phi of x to be x minus pi x times some other polynomial psi of x. Right? That's what it means that a polynomial has a root. So you see, what happened here is that phi was a prime polynomial. It means, in particular, it has no roots over the field f. And now I took this mod phi arithmetic field, k, and suddenly over this field k, phi has a root. And this field k is an extension of the field f. I mean, it contains a copy of f inside it. So what I did, in fact, is like is something very similar to when you pass from R into C. I mean, okay, but right? I mean, here in R, you can look at the polynomial x squared plus 1, and once you this is a prime polynomial over R, but once you add a root, I mean, in C it decomposes as x minus I, x plus I. So you can ask how did people think about, I mean, about C. One way to view it is this this kind of meta trick. So I know it's a delicate matter. So yeah, I'm glad you I'm glad you like it. Yeah. Any questions? Now, what do you think? You follow?
Yes, thanks for the clarification. And like this last thing, well, it was reminding me a bit of something that we saw, but I don't remember exactly the name. Like this thing of like that you can decompose things. I mean, now this like you have this phi of x equals to x minus p of x multiplied by this other symbol, which I don't know. This other symbol, you can keep doing this recursively.
Yeah,
So
I mean,
we did this not with polynomials, but with I mean not with this setting, but we did something similar to prove. I don't remember what, like that we could decompose things into prime polynomials. So I guess that we are heading towards the similar direction, but in this new setting.
but okay, but it's important that you get this meta trick. I mean, that in this new field K, I suddenly have a root for phi. Phi did not have any root in the original field, and now I enlarge the field in a way that forces phi to have a root. It's kind of
Yeah, that's very cool.
okay. And so maybe now is a good time for a break. We'll come back after the break and we'll see some application of this. All right, so the field F to be the real numbers. And you take the polynomial phi to be x squared plus 1. Then a phi is prime because it doesn't have any root in R. And now I consider polynomials over the real numbers modulo x squared plus 1. And this as a set, it is simply the set of all possible remainder polynomials. I mean, a0 plus a1x, where here I allow a0 and a1, they could be it could be 0. So in general, this is all the expressions a0 plus a1x, where a0 and a1 are elements in R. And now I consider the I mean the element x in this set, and if I do so, if I do x squared, or x times x, then this is equal to -1 modulo phi, right? Because x squared plus 1 is equal to 0 modulo phi. So what I get is that it's the set of all expressions a0 plus a1x, such that x squared is equal to -1. And of course, this is the same as, I mean, it's just a different notation for what we know to be the field of complex numbers, namely the set of all expressions of the form a0 plus a1i, a0 and a1 are real numbers, such that, of course, the I squared is equal to -1. Okay, so this what we did before the break in this example would give you the at least one way to obtain naturally the complex numbers from the real numbers. Any questions?
Why do sorry? Why do we prefer talking about complex numbers instead of this field
Instead of finite fields?
of this one?
Sorry, can you repeat the question?
Why do we talk about the complex numbers instead of talking about Rx divided by x squared plus 1 in that case?
It's isomorphic. I mean, it's
You know, I can see it. It just
yeah. Well, I mean, you know, the way people learn about the complex numbers is usually it's in earlier stages of the mathematical corpus. So it's easier to just define complex numbers like this with this imaginary number and define the addition and multiplication and start doing stuff with this. But in fact, from a more advanced, mature perspective, what we're doing here is we're modding out by a prime polynomial, and this means that we're adding up a root of this polynomial.
yeah.
Okay.
Thanks a lot.
Okay. So this brings us to the following definition. Let F be a field, and Fx a polynomial over F. A splitting field of F over, of course, capital F is a field K, or actually is a field, maybe we call it E, containing F, such that when we view Fx now in E of X, it decomposes into linear factors And so linear factors, I really mean that then f of x over e would be some constant, let's say alpha, times x minus alpha 1 times x minus alpha n, where n is the degree of f. Right? So alpha and alpha 1 up to alpha n are elements now in E. I mean, they are roots of this polynomial that possibly did not exist in F, but they do exist in E. So a splitting field is a field extending F such that the polynomial decomposes to linear factors, and E is minimal with respect to this property. And this minimal means that if K contains F and the polynomial f of x decomposes into linear factors over K, then E is minimal, so K must contain E. Okay, it's a bit long definition, but I hope it's clear. Any questions? And we have a toy example, of course. C is a splitting field of x squared plus 1 over R. Yes.
In the bracket, K is the same that was E above, right?
There are many brackets. So
the last one, where it is like if f is in K and f of x decomposes into linear vectors over K, this is what in the abstract above, K is what in the abstract above we called E.
Is no, I mean, okay, in a way, but this is just explaining what does it mean that E is minimal with respect to this property. I mean, if you have any other field containing F, I mean, if you have any other field K containing F such that the polynomial fx decomposes into linear factors over this K, then K must contain E. I mean, you cannot do I mean, E is minimal, right? Minimal with respect to inclusion.
Okay.
Okay, so because here, so maybe it's worth seeing this example. I mean, I claim that C is a splitting field of x squared plus 1. This is this f of x over R. Now, you need to be a bit careful in reasoning about it, because, well, the easy effect, of course, over C, f of x, you can write it as x minus I, x plus I. So over C, indeed, f splits into linear factors, but that's still not showing that it is a splitting field, because we have to show minimality. For minimality, if K contains R and F splits over K, of course, since F is a monic polynomial, i.e. f of x would be equal to, let's say, x minus alpha, and of course, the other thing is going to be x plus alpha. Then alpha square is going to be 1. Sorry, alpha square is going to be minus 1, because alpha is a root. I mean, alpha square plus 1 equal to 0 is equivalent to say that alpha square is equal to minus 1. So this alpha is, I mean, as far as the addition and multiplication goes, this alpha is the same as I. And since K is a field, it must contain all expressions the form let's say A0 plus A1 alpha for A0, A1 in R. Right? Because a field is closed under addition and under multiplication. So in fact, this would mean that K contains an isomorphic copy of C. I mean, essentially C. So C is really minimal with respect to this property. Is this clear? What do you think, Lisa?
Kind of.
Well, it's better if it would be completely clear. I mean, look, this alpha, I just call it alpha for distinction, but it really has to be, it really has to be I. I mean, it is an element satisfying alpha square plus 1 equals 0. I mean, or alpha square equals minus 1. So alpha is just another name for I, right? And once I have this a field containing I, and containing R, so maybe it's better to call this alpha I and then I mean, of course, if I have a field containing I and containing R, it has to contain all the expressions of the form A0 plus A1I.
Yes,
Right?
it's clear.
So it must contain C. Whatever it is, whatever K is, it contains I and it contains R, then it must contain C. So this tells you that C is the minimal field with respect to inclusion that for which this polynomial fx splits into linear factors. Okay, and this really this shows that that C is the splitting field of the polynomial x squared plus 1 over R. Okay, remember we need two things. Splitting field is a field for which the polynomial splits to linear factors, and it is the minimal field that that this happens. Other questions? What I'm trying to think what might not be clear here. Okay, let's try a proposition. Now, of course, this definition is nice. We saw even an example, but we are not guaranteed that a splitting field always exists, right? And this is the content of the next proposition. Let F be a field. And fx some polynomial. Then there exists a splitting field of F over capital F. Okay, so let us decompose F into prime factors over the original field big F. So I write f of x equals f1 of x multiplied by f, let's say, k of x. Now, if all of these factors are linear, if f1 up to fk are all linear, then the original field is a splitting field. Of F, right? I mean, it is a field in which F splits into linear factors, and it is the minimal field containing F, because I mean, of course you cannot do anything smaller. Otherwise, without loss of generality, suppose the degree of F1 is bigger than 1. Consider K1 to be polynomials over F modulo F1. And in this K1, we know that F1x has a root in K1. Let's call it alpha for or maybe, yeah, say alpha. Right? This is the meta trick we talked about before the break. This means that I can write F1 as x minus alpha times some G1. Some G1x in K1x. Now I can consider we can consider Fx over as a polynomial as a polynomial over K1. And as such, it has at least one linear factor. Right? Because I can write, I mean, whatever I could write in F, I can write in K1, because K1 contains F. So I could write in F the polynomial f of x being the product of F1 up to Fk. And now over K1, I can write F1 as x minus alpha times G1, and the rest I leave the same. So F2 of x up to Fk of x. And by doing this, I mean, I can repeat. Now I take, I mean, if G1x is not linear, we repeat the process. To get K2 that contains K1 in which I would have another, at least one other root, let's say beta of F. Since F can have at most a finite number of roots, this process terminates. So it terminates in some field K containing F, such that indeed F decomposes into linear factors. So I can write really alpha times x minus alpha 1 up to x minus alpha 2, sorry, alpha n, where the alphas are elements in K. And now, for minimality, observe that I mean K1 is the minimal field containing F and containing alpha. Because remember, what is alpha? Alpha is this pi of x, right? This and let me just scroll back to this this part. Right, I took a polynomial phi, let's say it was prime, and I constructed K, and then suddenly phi, when viewed as a polynomial over K, had a root pi of x. This, I mean, this K is the minimal field containing the original field F and the root pi of x. Because what is this? I mean, what is this K? K is all the possible remainders. And once you know that K contains, I mean, pi x is simply x. So once you know that you have a field containing f and containing x, it must contain x squared, it must contain x cubed and so on. It must contain alpha times x and alpha times x squared for alpha in f, because it is a field. So in fact, it must contain all the remainder polynomials. So K is the minimal field for which this happens. And so the same goes here. I mean, for minimality, observe that K1 is the minimal field containing f and alpha. Okay, so this and in every so K, all in all, K would be would be by induction. The minimal field containing all containing f and all the roots of fx. Okay, so this means that this K would be a splitting field for f for the polynomial. Okay, so I understand this is a kind of a more abstract than what we've done so far in the previous lectures. How do you feel about it? It's clear the minimality is also okay. Okay, so let me just I repeat the argument for minimality. I repeat it here in this example that we did here. I mean, I took a field f. I took a field f, and I took a prime polynomial. And now I constructed this field K that is the set of all possible remainders of mod phi long division. And this K, we showed that this K contains an element, namely the polynomial. So do I have like I mean, K is the set of all remainder polynomials, so all expressions of the form A0 plus A1x up to AK x to the K for some coefficients. I mean, A0 up to AK in F. And in this field, this new field K, we can look at the polynomial x, and x suddenly is a root of phi over this field K. But if you look at it, this construction is the minimal thing that you could have done if you wanted a field that contains F and contains X, because once it contains F, it contains, I mean, all the constant remainder, all the constant remainder polynomials. And once it contains X, it must contain all scalars times X, and all powers of X, and all sums of these expressions. So it must contain K. So in fact, K is the minimal field for which which contains F and contains the root pi x. And by this argument, I mean, you apply it in this proposition. I mean, in this proposition, every time we split a factor, we know that what we did is the minimal thing that you could have done. So this shows you that all in all, the resulting field K1 was the minimal for which the first root was constructed, and eventually the resulting field K is the minimal one that that can contain all the roots of the original polynomial. Okay, so now would be a good time for questions, comments, requests for next time, and so on. All right. Then we continue next time with this splitting field stuff. What will happen, I'll just kind of overview of what's coming up. We are going to prove that splitting fields are in fact unique up to isomorphism. And once we know that splitting fields are unique up to isomorphism, we will able to very quickly, very easily classify all finite fields. So that's what's coming up. All right. So hope you enjoyed, and have a good rest of your day.
Thank you.
Thank you. Thank you.
Thank you. Bye.
Thanks. Bye.